Anyways, let's get started with today's set of problems. We're going to be working on the first one, which is actually the last one in our week 2 study list, clone graph. Given the reference of a node in a connected undirected graph, return a deep copy, deep clone, of the graph. Each node contains a value and a list of its neighbors. Okay. So, seems like probably have to do some sort of graph traversal here. Right. The main question I guess I have is how do we avoid, I guess, removing, or how do we avoid adding duplicate nodes? And how do we establish the same adjacencies? I believe I've done this problem before a long time ago, similar to the yesterday's problems, level order traversal of binary tree and threesome, but this one I have lost all sort of semblance of trying to remember what I actually did. Let me think about this. So you start at some node. For each of their connections, we need to create that new node, right? But this is only because we know they do not exist. So how do we know if some node exists? Well, we can maybe recursively calling the node. We can add at least a... When we recursively call a node, we can at least know the root or the origin. Hold on 1 second. Okay, that was a false alarm. So we can at least know the origin, but we don't really have a great way of knowing sort of all of the nodes that exist. I wonder, are all the nodes guaranteed to be unique? The value is unique for each node. Unique for each node, and the range is 1 to 100. In that case, we might be able to do something fancy. Well, not that fancy, but let me think. Something that we could consider is that then because this is the case, if a node has a value that matches, because is this an adjacency list of values or is this okay. If a node has a value, then it must be the node that needs the connection. basically, if we go through node 1, we know that we have nodes 2 and 4 as adjacent, and so we create them. Now in node 2, we have adjacencies to node 1 and 3, but because we know we've seen this node 1 before somewhere else, and because these values are unique to the graph, that means that we can safely assume that this reference, this node reference with a value of 1 is the node that we need to connect to. So what I'm thinking now is that because the number of values that we have that are possible is so low, we could probably get away with creating an array of size 100 of node references. And we populate those node references once we actually get a node value. So that means that if a node exists within, so what we'll do is that we'll start at some node within the original graph, and we'll also clone that root. For each of the connections within the original graph, if a node does not exist, create it and add it to the array. Then establish the appropriate connections and add them to the next round of nodes to populate with a its connections. So this will kind of be like a, what I'll say is like a BFS style approach. And in this case, because we are going to be going through, so we'll go through 1, then 2, 4, then, what can we do to make sure if a node is quote-unquote complete? Well, when we visit a node, we will either establish the connections or create the nodes and establish the connections. Therefore, we need to visit all of the nodes at least once to establish those connections. So I think I'm leaning towards an O of n runtime, where n is the number of nodes in our original graph. That's sort of where I would put it at the moment. And of course we would need O of n space because of the clone, right? There's no way we can get around that. So let's actually give this a try. So we can say val q is equal to mutable list of, and we can say node. This will be for sure a non-nullable queue of nodes. And we'll add the root or the node to it, I guess, because it's, why is this like, I don't know. I guess it's technically not the root. There is no root in the graph, right? But it's the main one. And we know from here that there is at potentially no nodes. So if node is null, then we can just return null in general. There's no point in doing so. There's no point in running the rest of our algorithm if that is the case. So we create a queue which has a node within it. We will also create our reference array, which will be an array of node question mark, which will have a size of 99. Actually 100. Because we have potentially 100 nodes, right? Because the values can go between 1 and 100. And let's continue on from there. So this reference array exists mainly so we can make our connections and sort of keep track of what nodes that we've seen before. We will also create our clone root, I'll call it, is equal to a new node. Actually, do we need to let's see. Let's hold off on this and we'll create a private late init var clone node. Then we'll say while the queue of the original node is not empty, we can say our front is going to be queued front, and we can say queue remove at 0. We'll just remove it there. Then we can say if our front node is our initial node, then we do something. Then we'll say clone node is. We will first start by creating our actual node. So val clone node is equal to a new node of type or of value equal to the front dot val. Let me think. This is a list. Apparently it's an array list in its definition, which probably means, and this is probably just taken from Java, so the Kotlin docs, looks like the Kotlin docs does have some stuff. I think we can just add to it, right? Awesome, okay. And we'll just create an empty list for now, right? We just need to declare, or we just need to supply the initial value of it. If this happens to be the first node, then we can say clone node, or clone root, we'll say, is equal to clone node. And then we can say front.forEach so for each node within our original reference, if reference array get or null at our node.val, and since this is an array of size 100, it'll go 0 to 99. And since our values go from 1 to 100, then we need to subtract 1. So if get or null at this index is not null, so that it exists, then we can say our clone node dot neighbors add our node. Otherwise, we will simply add the node into our, or we will first clone it, we will create it, and then we'll add it. So we'll say val new neighbor is going to be a node. Actually, no, because this will create, or this method already creates that clone when we add it to the queue. However, in doing so, we can't actually establish the neighbors now, because otherwise, when we visit them, they will get cloned again. So I think rather than doing that, we can create our clone root here. And we won't create any clones while we are inside this loop. All we will do is that we will take whatever node is here, we will create the neighbors if they don't exist, and we will link them. So we create this new neighbor if it doesn't exist within our reference. Then we will say our reference array at node dot val -1 is equal to our new neighbor. We will add it into here. So clone node neighbors add our new neighbor reference. And then within our queue, we will also add that new neighbor in order to explore it and populate its neighbors. So the idea is that we start at 1. We see that we are connected to 2 and 4, and 2 and 4 don't exist within our graph yet. So we will create 2 and create the connection between 1 and 2. And then we will do the same thing for 4. We will also start by add 2 and then add 4 to our graph. In the next cycle, when we go through 2, we see that 1 already exists within our graph, and that is something that we will have to array at 0 is equal to clone root, right? So at 2, we have adjacencies to 1 and 3. We know that 1 already exists within our graph, so what we'll just do is just add it into our adjacency list. As for 3, since it doesn't exist yet, we will create this value 3, and then we will create our connection here. For 4, both of these are already created, so we'll just add them to our reference, and then we'll go on our way. Once we hit 3, since both of these are also already made, 2 and 4 already exist, we will add those references, and we have nothing else to add to our list. From there, the queue is now empty, and at the end, we should return our clone root. So this takes a little bit of extra space due to storing our nodes in this manner. However, I think it's worth it, because this way we know exactly which nodes do exist within our array, or within our problem set. We know which nodes that we've made, so we don't run into duplicates. And we start by creating the clone root. So let me just run through this. So if the node is null, we return null. We create a queue. We could also push this a little bit higher. And then we can also say if node, or if node, sorry, yeah, we can start here. If node dot neighbors dot size is 0, return clone root. So if all we have within our array is just this node with no neighbors, then we just return the root. Really, really, really minor optimization that probably won't matter too much. However, we actually do still need to actually, because this here, we need to move this down because we don't create a reference array until later. And we need to return the clone root, so we need to actually do that. This should just be node.val and not front.val now. So our clone root clones the root, or the node that we're starting off with. No neighbors, we return it. We create a queue and store this. This queue is for originals. So technically, I should call this like queue originals. Just so I have sort of more context as to what's going on. I think adding this, it's not a big deal in any case, but I think it's just nice to have a little bit of context of what's actually going in here. We create this queue of nodes, and this is node without nullables. We create a reference array because we know we are given that all values are unique. So if a node exists which holds a specific value, then we know that that is the neighbor that we need to connect to. There will not be another neighbor of the same value with that is a different reference. And then we add our initial clone root into this array. And we can't just do that. We need to do node.val -1, right? Because there's no guarantee that our node starts at 1 as far as... Oh, okay. Our given node will always be the first node with val is equal to 1. So we can actually do that. We can start with a value of 0 here, because we know that our node will always start as 1. While the queue is not empty, finally using is not empty for the first time. I'm not even sure if this is a method in 1.3 Kotlin. We'll see. We take the first element that's in our list of our queue of originals. Then for each of their neighbors, we will see... Oh, this clone node doesn't actually exist anymore. Val front clone should be equal to our reference array at node.val -1. Actually, this should be front.val. So we're getting the value here. So our front clone should already be created. So I'm just going to direct index here rather than calling get or null and creating the null if it doesn't exist. Though that can be something that you can consider. Then for each of the neighbors within our original node, if it exists, then we can just add it to our neighbors. If it does not exist, then we will create that node, add it to our reference array, add it to our neighbors list, and then queue its original value up. And we want to queue the original node and not the new neighbor, because the new neighbor does not have neighbors yet. It is still an empty array list. So we create, so first of all, if it doesn't exist, or if it does exist rather, so reference array, get our null, this -1 for each node is not null, then our front clone will just add it to our neighbors. We want to add a reference array at node.val -1 and not our original value. So our neighbors add, and we add this reference here. Otherwise, we create a new value with the node's value. Create a new node with the node's value, the original node's value. We add it into our array at the appropriate index. We add it to our neighbors list because it is one of our neighbors. And this should be front.neighbors, not just front for each. We want to add it. And then we want to queue up the original node for further exploration. Then we remove that our front node as we have fully explored it. And at the end, we return our clone root. So we actually caught a decent amount of mistakes, and I'm sure that there are probably a few more in here probably that I've missed. But I think going through the actual implementation line by line was really helpful in helping me sort of identify like, oh, this is a careless mistake here, this is a careless mistake here, this is a careless mistake here. I should have done this, I should have done this. Or rather, this is the right value, this is the right value of what I actually meant. So maybe something to consider for the interview as well once I start doing those. So I think this is actually a good point. I've reviewed the code. I've talked about the runtime. I think we can give it a shot with our first graph. And let's see how it runs. It's probably some compile time error that I'm missing. No value passed through the parameter init. We will say let's just toss in a lambda that just passes in null. And I forget that in Kotlin, the list has a first, not a front. A front is exclusively for the queue, or I guess the deck within. Looks like we're not happy about this neighbors because it is an array list of node question mark. If node is not null. So we're just going to wrap this entire thing in a if node is not null statement so that hopefully the compiler is smart enough to know that within here then there is no null value for our code. Q originals add node. Otherwise, we will have to be a little bit more explicit about how we do things here. Our front clone is a reference array. Reference array is icy. Okay. Right, because our front clone technically is nullable. So we'll have to add those there. Is there anywhere else? I think that's it. No, it seems like the array list is also null. Why is the array list a null? That is something that I'm confused about. I guess technically it's like that, but the array list node has a default value. You really want me to add a question mark there too, Kotlin? That's odd. Then should I also add one here? Front clone. Is it because front clone could be null? But if front clone is a null, it won't run the rest of the statement. How can the neighbors also be nullable? And why isn't it nullable for the neighbors that we are given? At least it's not giving us a message here. Interesting. Anyways, it seems like it worked for our initial test case. Let's toss in 2 more test cases. And it looks like they worked. Okay, let's toss this through the ringer then. And let's run a submit on it. Okay, so our runtime is pretty good with a pretty average runtime of 42.35%. That seems reasonable. Our memory usage seems to be a little bit high, but let's see. If our memory usage is a little bit high, what could we do instead? Well, rather than using a list, we could consider using something from Java. So Q originals is equal to array. We can use a linked list from Java, I believe, which will allow us to insert items into the end and pull from the front relatively efficiently. However, I'm not sure if there's actually a way to do this. I'm not sure if this list actually has that much of an overhead. Well, we can see. And I'm not sure about linked list Java. I need to look at the documentation. Where is the Java documentation? Maybe if I type in documentation. Linked list. Here we go. Do we have an add, which adds in the front. So we don't need to change that. We won't have an is not empty. But do we have an is empty? We do have an is empty. So we'll have to change this to is empty and add a not there. Then do we have a front or first? Well, we can do a poll first. And we can then remove at. I think that's actually all we need to do to convert this from a mutable list into a linked list. Let's actually give this a run through our original code. Let's see. Infer type is node question mark. Right. It seems like it's not picking up on the fact that we handle this case. So let's throw in the double bang, which is a bit of a code smell, but we do know that if the node is null, we've already handled it. So this shouldn't be an issue. No, it seems like it's... Node question mark. Really? It's really really, really not liking that. Infer type is node question mark. Right, that is node. But mutable collection out node question mark. Collection, sure, was expected. Would it be happy if I did node question mark here then? Well, this returns either a, so I'm guessing this part will, so Java will probably scream at, or yeah, the compiler will probably scream at me now here. No, it still doesn't like this. Am I not allowed to add this in here? I don't think so. Construction empty list. Oh, I guess not, actually, yeah. In that case, I'll just do q originals.add node. It seems like for Java's collections, you can't directly add stuff in here and it'll and have it just magically be inserted into here. I guess that's a what is it? Syntactic sugar from the Kotlin team, which is nice. Okay, let's give this a submit and let's see if this linked list implementation is actually faster. It would be funny if it actually isn't. No, it actually is like much slower. That is surprising. Wow. Okay then. How else then can we actually speed this up? I mean, to be fair, like, this implementation of the solution, I honestly don't think is that bad. We're using mostly Kotlin-based, a Kotlin-based solution. Sure, the memory usage is a little bit high, but maybe the memory usage is not within the list itself, or at least the runtime as well. But maybe the issue happens somewhere else. Do we need to use an array of size 100? Off the top of my head, I think an array is fine. We could of course use a map instead, but I imagine that using a map would actually be slower. Because we're not adding anything to the array, we know that at maximum size it will be 100. So all we are doing is indexing within the array. And honestly, I think that's pretty fast compared to, I mean, like retrieving an array, an item from an array if you know the index, is the same constant time as retrieving an item from the map. And in the map situation, if we have a bad hashing function, then it would actually be slower. So I'm honestly curious. I'm gonna be looking at the solutions to see how they actually sped this or made this use less memory. I don't think that you can really have that much of a change in memory. But in any case, I think that's going to be it for this problem. So our original solution, which was our best, was 42.35% runtime. And I think it was like 5%, somewhere in the neighborhood of 5% of memory. In any case, that's going to be it for this video. I hope you learned something, and I will see you for the next problem.